Hi, my name is Sher and I'm an SAT math tutor. Last time you saw me do the Oxford MAT Part 1. Today I'll be doing Parts 2 and 3. If you like watching these sorts of videos, be sure to subscribe so you get notified whenever new videos come out. Alright, let's move on to Section 2. So let's look at Section 2. Functions f and g are defined for positive integers n. This is f, this is g. A set of positive integers that can be achieved by applying in some order a combination of f and g's to 1. Okay, let's look at part 1. Write out the binary expansion of 100. Well, that doesn't seem very fair. That kind of gives advantage to computer science students. So, at least they gave an example here. 13 is 2 to the power of 3 plus 2 to the power of 2 plus 2 to the power of 0. So, 100 is 64 plus 32, which is 96, so plus another 4. 2 to the power of 6, 2 to the power of 5, and 2 to the power of 2. So if we write it from backwards, 0, 1, 2, 3, 4, 5, 6. That's it. 1, 1, 0, 0, 1, 0, 0. Alright. Show that 100 is in X by describing explicitly a combination of F's and G's. Do I have to try everyone? Okay. G is specifically a multiple of 4 and Fn is just odd. It's just odd. Alright, so we're just going to work backwards, I guess. 100, so before 100 probably have G because 100 is a multiple of 4 times 25. 25 is odd, so before G it was F, which is 12. 12 times 2 plus 1 is 25, and before 12 it was G again because 12 is a multiple of 4, so we would have 3, and 3 is an odd number, so it would be F again, which is fun. Perfect. So 1 times 2 plus 1 is 3, and then times 4 you get 12, times 2 plus 1, 25, times 4 is 100. Show that 200 is not in GS. Okay, so 200, if we go backwards, is G50 because multiple of 4, and G is 50 is not a multiple of 4. 50 is not. Do I have to write everything here, the small spaces? Multiple of 4, nor odd. 50 cannot be created. 50 cannot be created by G or F. Be the output of G or F. Alright. Show that if n is in S, then there's only one combination of applying. Output of F are always odd. Output of G is always a multiple of 4. A number cannot. Output of G is always 4. Always multiple of 4. A number cannot be both odd or multiple of 4. Or a multiple of 4, so hence there's only one function to apply at a time. Hence only one function at a time can lead to its creation. Function at a time can lead to its creation. So yeah, that's it. You only can use F or G at a single time. You can't use either F or G, but F and G only. Alright. Let's look at this. You carry the number of elements of n of S that lie in the range 2k. There is not enough space here. Do I have space? Do they put it somewhere here? Is this where I'm supposed to write everything? It's just all blank. Okay, yep, I guess I was supposed to write here. Alright. Anyway, part 5. UK plus 2 equals to Okay, hopefully I've got enough space for all of that. Okay, so let's try to see. So we need to prove that UK plus 2 must equal to UK plus 1 plus UK. Oh, and also we have UK is, what is UK? 2k less than equal to n less than equal to 2k plus 1. 2k is less than equal to n, which is less than 2k plus 1. So I guess I probably should start with finding what's UK and what's UK plus 1 and UK plus 2. Alright, UK plus 1 would be 2k plus 1 is less than equal to n, which is less than 2k plus 2. Oh no, my computer's being a bit laggy. And the last one, UK plus 2 is 2k plus 2 and 2k plus 3. Right, basically I gotta make UK, all these become like this. So if I want to make k become k plus 2, I probably should apply some function g, the function g. So from UK, if I do g, and then now I should get 2k plus 2 is less than equal to gn, which is less than 2k plus 3. Perfect. So basically what this question is saying, so the solution equals to the if you apply UK and you make it undergo function g, you get all the multiples of 4s plus, and I guess this one's going to be the odd numbers. So if I want that to be odd numbers, it's probably going to be f then 2 times 2 plus 1, k plus 2 plus 1 is less than equal to f and 2k plus 3 plus 1. It doesn't look exactly like it though. But these are all just odd numbers, I see. Alright, so even if we did make it 2k plus 1 only, it wouldn't have counted 2k plus 1, so it doesn't matter. This one, it doesn't include, so technically I can just change it to this, minus 1. So this would be the number that it includes. It includes from this number to this number, which this fits within here. So let me just write out the proper reasoning. When we apply gn to, what's the proper way to phrase it, to the to elements of n in, okay, to elements of n in UK, we get the multiples of 4 present in UK plus 2. When we apply Fn to elements of n in UK plus 1, we get the odd, I should have put the word elements here, elements present in UK plus 2. Hence, UK plus 2 must equal to UK, which is all the multiples of 4, plus UK plus 1, which will give you all the odd numbers. Alright, and what's the next one? Also very similar, so SK plus 2 is, but now this is 1 to k plus 1. Okay, so I guess the same thing. Let's just write out what we have to prove first. SK plus 2 must equal to SK 2k plus 1 plus sk plus 1, and we know sk is, what is sk? Alright, 1 and 2k plus 1. 1, 2, 2k plus 1. So obviously we should write out again sk plus 1 and sk plus 2. So this is 1, 2, and 2, 2k plus 2, and this is 1, 2, and 2, 2k plus 3. Alright, obviously we need to make k plus 1 become k plus 3, so same thing, apply the function g. For is less than equal to n is less than 2 k plus 3, because we multiply everything by 4. If we apply the function n here, we would have times 2 plus 1. So 1 times 2 plus 1 is 3. It's less than equal to n, which is less than 2k plus 3 plus 1. Again, same thing, it doesn't include this, so if I change this to include, we have to put minus 1 instead. Oh, and I guess if we have this, I guess 1 is included as a function as well, so if we do not count 1, that one of the solution sets as 1, technically 2 would be you can't use 2, 2 is not a number. 2 is not one of the numbers that would exist, 1 is, 2 is not, so that's why sk plus 2, okay, so sk plus 2 minus 1 would equal to sk plus 1 plus sk, for very similar reasons like earlier, because sk, when we apply, let me just write out the reasoning again, when we apply gn to elements in sk, we get the multiple. Alright, so let's look at part 4. So show that if n is in S, there is only one combination of applying f's and g's in order to achieve n. So for example, 67 can only be achieved by applying g, then f in that order. Okay, so I mean, we already know that fn is always odd and g is always a multiple of 4. So how do we write it? Output of f is always odd. Output of g is always multiple of 4. I mean, not perfect English, but it doesn't matter. This is a math test. Is always a multiple of 4. How am I supposed to fill in everything here? Of 4. A number cannot be both. Both odd and a multiple of 4. Hence only one function can be applied at a time. One be used to create it. Actually, there's a better way to generate the number. Alright, let's look at V. So let uk be the number of elements of n of S that lie in this range. Show this. Is there any more space? Oh, okay, I guess we're supposed to fill it in here. Oh, I've got how many pages to fill it in? 1, 2, 3. I've got 3 whole pages. I should have written it there. Alright, let's look at part 5. So we have to prove that uk plus 2 must equal to uk plus 1 plus uk. What is all this? Alright, it is this number of elements of n that lie in this range. Okay, let me write that down so we don't forget. uk is 2, what was it? K and k plus 1. uk is less than equal to n, which is less than 2k plus 1. So if I want to figure out the rest, uk plus 1 is 2k plus 1 less than equal to n less than 2k plus 2, and so uk plus 2 is 2k plus 2 less than equal to n less than 2k plus 3. I need to show that the number of terms in this is equivalent to this plus this. I guess my first step would be to show that, would be to make uk look the same as this, so using one of the functions. We've got 4, either times 4 or times 2 plus 1. So if I want k to become k plus 2, I probably should apply the g function. So for uk, if we apply some g function, you have 2k plus 2 is gn, and then 2k plus 3. Perfect. So basically, if we take any answer from uk and we apply the g function, we would get basically all the multiples of 4s that are in here. We will only get multiples of 4. So I better put that down so I don't forget. Multiples of 4 in this, so I don't forget. And what about this? So if I have to probably apply f, if we apply f, we would get 2k plus 2 plus 1 is less than equal to fn is less than 2k plus 3 plus 1. This is all multiples, all odd numbers here. So technically I need 2k plus 2 and 2k plus 3. This is plus, oh, it doesn't include this plus 1, so the next number it will include is the one less than it, because 2k to the power of 2 to the power of k plus 3 is even, so it has to be 2k to the power of k plus 3 minus 1. This would make it odd. So it counts from this number to this number. And anyway, it doesn't even include, an odd number wouldn't include 2 to the power of k plus 2. That's already concluded here. So basically, if I want to explain it, because I have to explain it, when we apply the gn function to elements in uk, we will get multiples of 4 present in uk plus 2, and then the same thing for k plus 1. When we apply the f function to elements in uk plus 1, we will get odd numbers present in uk plus 2. Hence, uk plus 2 equals to uk plus 1 plus uk plus 2, because all the odd numbers and all the multiples of 4 will give you all the possible number of numbers, if that makes any sense. Alright, and let's look at this other one. Let sk be the number of elements of n. It's very similar, I just have to do the same thing, but it's a bit different. So that is part what? Part 6 vi. So I have to show that sk plus 2 equals to sk plus 1 plus sk plus 1 outside right here. Alright, so what was it? What did I have? 1 to 2 to the power of k plus 1. So basically, if I've got sk, which lies between 1 to n, to 2k plus 1, so that means sk plus 1 is 1 is to n is to 2k plus 2, and sk k plus 2 is 1 is to n is to 2k plus 3. So basically, make this look like that again. We apply the g function again. G means times 4, so 4 is less than n is less than 2k plus 3. Same, this one probably is f again. 1 times 2 plus 1 is going to be 3, and 2k plus 3. So there we go. Oh, forgot the minus 1, so it will change to equals to. The reason is because if we put plus 1, it does not include this number, and 2 to the power of k plus 3 is even, so we're not even going to count that as well, so that's why it includes all the way to the number before 2 to the power of k plus 3. Alright, so essentially, just around the reasoning again. Wait a second, there's a plus 1 there, we can't just write plus 1. Oh, because this is 1 and we have to include 1, I see. Okay, so when g is applied to elements in SK, we obtain the multiples of 4 elements present in SK plus 2, and then write the same thing for SK plus 1, except it doesn't include 1, so like it has to add 1. So when, not G, when F is applied to elements in SK plus 1, we obtain the odd elements excluding 1 present in SK plus 2. So that's why SK plus 2 minus 1, because it's missing an element, will equal to SK plus 1 plus SK. And hence SK plus 2 must equal to SK plus 1 plus SK plus 1. I think that's how we proved. Alright, the proving part was annoying, though, I will admit that. So alright, let's look at question 3. So apparently you're supposed to do question 3 if you are applying for one of these courses. So I'm just going to pretend that I am applying for the mathematics course, so I will have to do question 3. Alright, let's look at this one. What are the values of a and b? Well, a and b are x-intercepts, so clearly if they're x-intercepts, we're going to have to plug in y as 0. So let me write down the original question first so I don't forget. So part 1, y squared minus y equals to x cubed minus x. So when I plug in y as 0, I have 0 equals to x cubed minus x. 0 equals to, factorize out the GCF, complete the square. I get x equals to 0, negative 1, and positive 1. And a and b, a is negative, b is positive, so a is clearly negative 1, b is the positive 1, and this is our 0. So write that in, a equals negative 1, b equals positive 1. Alright, what about part 2? By completing the square or otherwise, find the value of delta. Where is delta? Oh, these ones. So just by looking, the slope at delta, these points, are undefined. So you can just use differentiation to find it. So undefined slope, we would have to, since it's undefined, we're not going to do dy dx, we're going to do dx dy. So here's our equation. If we differentiate that, 2y minus 1 equals to 3x squared dx dy minus dx over dy. If we let dx over dy be 0, since it's an undefined slope, it's going to be 2y minus 1 equals to 0, y equals to 1/2, so your delta must be 1/2. That's it. Part 3. Explain why the curve is symmetrical about that line. Because this. Okay, great, I'm going to have to complete the square then. I didn't want to, but alright, we have to do that. So part 3, for y squared minus y equals to x cubed minus x. If we complete the square here, y minus 1/2 squared minus 1/4 equals to x cubed minus x. Y minus half equals to x cubed minus x plus a quarter. Square root of that with a plus minus sign. Y equals to 1/2 plus minus square root x cubed minus x plus a quarter. So we're going to have to talk in terms of that first. So for y equals to plus minus, actually we don't need for. This is, so we know this graph itself is symmetrical about y equals to 0. So when a translation half units upwards occur, y 1/2 plus minus cube square root x cubed minus x plus 1/4 will be symmetrical about y equals to 1/2, which equals to delta. That's it. Okay, and let's look at part 4. What do they want for part 4? Find the cubic equation in x which has roots those. Well, it's literally this line intersect the graph. So we have part 4. We have y equals to 1/2. If we plug in y as 1/2, 1/4 minus 1/2 equals to x cubed minus x. We'll just get 0 equals to x cubed minus x plus a quarter. That's it. That's our function. Number 5. By factorizing this cubic, find the value of that. Alright, so if we actually want to compare this, x minus alpha times x minus beta times x minus gamma equals to 0. If we follow that, we will have x squared minus alpha plus beta x plus alpha beta times x minus gamma equals to 0. And if we follow that, we'll have x cubed beta and then minus alpha plus beta plus gamma x square plus alpha beta plus alpha gamma plus beta gamma x plus minus alpha beta gamma equals to 0. So what do they want us to look for? Alpha plus beta plus gamma, which is this one, x squared. There's no x squared here, so clearly by comparing a coefficient of x squared, so here is my x squared and this one has no x squared, so obviously alpha plus beta plus gamma equals to 0. Alright, and then what's our next problem? By considering, I just did that one. We have a circle C which has points this and this as the ends of the diameter. Write down the equation of C. Show that C intersects S at 2 other points and write their common x coordinate in terms of y. So we have another circle right here. So we've got a circle. I'm not sure what circle. I'm going to try my best. It looks like this. I guess they intersect about here. I'm not sure what that is, but we'll try to work that out. Write down the equation of C. So obviously alpha beta minus alpha is the diameter, so the radius. I'm going to have to use more space. So part 3, part 4, VI here. So the radius is just beta minus alpha divided by 2, because beta minus alpha is the diameter, so beta minus alpha divided by 2 is the radius, and the center is, it's the average of these two. So, well, the x coordinate for h would be alpha plus beta divided by 2. So if we plug it into the equation of a circle, x minus alpha plus beta over 2 squared plus y minus, what's the x coordinate again? Delta. Oh wait, delta is 1/2, so minus 1/2 squared equals to our radius squared, beta minus alpha over 2 squared. This is the equation of our circle. And what's the next part? Show that this intersects S. Well, we already know y minus, so from here, y minus half squared is equal to this, so I can just replace that. X minus alpha plus beta over 2 squared plus x cubed minus x plus 1/4 has to equal to beta minus alpha over 2 squared. Alright, and what do they want us to find? Find the x coordinate. So let's just start by shifting everything to one side. So we've got x cubed minus x plus, and then we distribute that, x squared minus alpha plus beta x plus alpha plus beta over 2 square minus beta minus alpha over 2 square equals to 0. How would this help us in terms of gamma? Well, we know alpha plus beta plus gamma is 0. And, well, this is a cubic function. There will be 3 solutions to this. We already know 2 of the solutions, alpha and beta. We don't know the third one, so alpha plus beta plus some unknown theta would equal to, here, this is our x squared, -1. So if alpha plus beta, and we also know alpha plus beta plus gamma equals to 0. So if we subtract these two, gamma minus theta equals to 1. Theta equals to gamma minus 1. That's it. That's how we would show our answer. Alright, so that's it for section 3. And that's parts 2 and 3 of the Oxford MAT. Were they harder than section 1? Yes. But were they undoable? Not really. The proving part was annoying though. You have to write a lot of words. Did I expect to take this long? Not really, but I'm determined to see it through. So be sure to leave a like if you enjoyed the video and subscribe so you get notified when part 3 comes out. Thanks for watching.